Hi. Okay, so I'm going to talk today about information theory and the links of information theory to Jung's cognitive functions. And I guess the intro is going to be more about an intro to information theory, but it's not going to go too deep. I want to try to stay more on a surface level, and get to the links between all of the different places where it shows up. So if you're looking for a deep, like a really deep dive into information theory, this is not the video. I might make another video where I go a little deeper, but for now I just want to stay really on a surface level and go really broad and try to get a really broad picture of information theory. Okay, let's start this out. Okay, so if you've seen information theory videos, you might be seeing like these conspiracy theory type videos where, you got the simulation hypothesis and the holographic principle, right? Simulation hypothesis, you'll see, is like the Matrix. The whole world is just digital. We're all just information. We're a simulation, right? So the universe is made of information, and that's all there is. It's just information, right? And information theories might agree with this, but we'll talk about that a bit later. And then the other mainstream conclusion that we see is the holographic principle, right? You see that a 3D object is actually just a hologram of a 2D surface it projects it out like that, okay? So like the black hole, for example, the surface of the black hole contains the same amount of information as the contents of the black hole, right? So there's that kind of thing. So both of them sort of cross-link and support each other, but okay, so we're not gonna start from there and prove that here. My sound just spiked. Okay, so we're not going to prove that here. We're not going to try to get there. We're just going to try to get a broad understanding of information theory and not jump to any conclusions like this. So if you want to support your view that the universe is really just a simulation, this is not the video for you. But if you want to understand why some people say it might be, so yeah, this might be. Okay, all right. So, okay, information theory. Now, it comes from a few different places. We see it everywhere, and that's why it's just it permeates all of physics, I guess. And the main two places we'll see is quantum physics and thermodynamics, but also like astrophysics with black holes, which is also an extension of thermodynamics. But I mean, so I'm not going to go too deep into quantum physics, but I'll just show. Okay, so quantum physics, you have quanta as indivisible packets of energy, which are information. Okay, we say quanta are packets of information as well. And we have the fact that observation affects results. Now, this isn't apparent how the connection is here, so I'm going to make the connection for you guys. The thing is, when you observe something, you're taking information out of it. Okay, that's how observations work. Okay, so in order to observe something, you need to transfer information into your brain or to a device that can be displayed on a screen with photo multipliers or something, right? So you're always transferring information. That's how you get information from one place to another. And so these quantum particles are so small and so delicate that if you take information out of them, you're really affecting them, okay? You're really affecting the results, okay? So that's how we get observation is affecting results, because really you're taking information out, and thus there's, depending on the type of information you're taking out, and we'll get into information types soon enough, you'll affect it in a different way, okay? You'll collapse the wave function in a different way, okay? And then we have thermodynamics, we have entropy. I don't want to get too deep into entropy. Entropy is like a really fascinating subject. Entropy talks about the structure of information and how it's structured. So we'll see later that if you look at information in one domain and then you go to another domain, it's random in both domains. In one domain, it'll be random in the other domain, right? Whereas if it appears random in one domain, you look to another domain. We'll get into it, but entropy is more like a broad thermodynamic concept that I really want to talk about as well. It's really fascinating to me, but not all in this video. But for now, yeah. Also, if you want to create information or have information, it's information is low entropy, and you need to increase entropy in other places. So like that's why your computer is hot, is warm. It heats up when it does calculations, is because of this, because it's calculating, it's dealing with information, and it has to increase entropy by heating up the world around it, right? And same thing, black holes, I said this again, black holes are maximum density where the surface can still contain all information, right? We said that before and when we talked about here, okay? All right, reality. Okay, so yeah, let's not get carried away. Let's like look at what reality really is saying here, okay? So first of all, we have no way of knowing, okay? And we won't ever know if the universe is really just information or something greater, okay? Now this is a conclusion and I'm going to get there, but the reason is that consciousness is information processing, all right? That's what our consciousness is. We are processing information. And we can't understand anything beyond information. That's the only thing we can ever hope to understand, right? And so if the universe is much more than just information, we won't know that. We can't know that because the only thing we can get out of the universe and into our cognition and into our minds is information. So for us, for all extents and purposes, the universe is just information. We can't understand anything beyond that, right? The universe could be something far more complex that we have no idea. It could be, I don't know, it could be mush that isn't information that's this, I don't know. I have no idea what it could be because it's not possible for me to know, right? The only thing I can ever know about the universe is information. And the only way I can get that information is to extract it from the universe in some way, okay? So that's why we say, so when information theory comes along and says the universe is nothing but information, well, could be. That's the only thing we can ever really say about it, right? And so what information theory says then is the deepest understanding we can ever get about the universe, the deepest we can ever understand the universe is the structure of information itself, okay? Everything is going to come to us in information in some form or another. And when we understand the structure of information, that's the deepest we can understand because all of the information that comes to us that's the atom, right? The atom is this indivisible thing, right? So the indivisible thing that the universe has that we can understand is information itself. And that's why when you look at information theory, it's just so broad. It envelops everything, right? Because for us, it is everything, okay? I hope I explained that well enough. Okay, so fields of study. All right, so we have systems, signals, like analog signals and things, and then you have digital signal processing. You have a particle wave duality, and you have mathematics. You have the Fourier series and the Fourier Transform. Okay, if that didn't mean anything to you, that's fine. It doesn't matter. What matters here is, look, you see this wave here? This wave has a specific frequency. It's represented here. This wave here has a specific frequency. It's represented here. This wave here has a specific frequency, right? So if you look at it in terms of amplitude in time or in space, you'll see this big mess and jumbled mess, right? And the Fourier transform is based on the Fourier series. It's an integral. It'll transform one type of information, this type of information, to this type of information, and I'm gonna go deeper into this because this is the fundamentals of the structure of information itself. Okay, so the information structure in the universe that we can get to, it's not zeros and ones, it's frequencies, and it's how these frequencies add up together and represent themselves in the universe in this way. Okay. And so doing this transform, we can look at the information in a different way, right? And now, and the thing with this transform is, if this was frequency and we did the transform, it would be represented in time like this. And you'll see how this is true. So like, for example, like you see particles in the universe are like blips, right? We have these blips of particles in the universe. And so if we do a transform on it, we might see them like this, right? So just like, I'll go deeper in the next few slides. Okay, so this is the Fourier transform. So you have here as well, you have like this sort of square wave thing, right? What's the square wave? It's a sum of all of these different frequencies, right? You see this frequency, that frequency, that frequency, and it adds up to a square wave, right? So what you have with the Fourier transform is just this fundamental thing. If you get more and more accurate in one domain, right? So like this is super accurate, right? This is what we call the delta function, okay? This is the delta function in time. And what happens in frequency is just spread out completely. It's just like this straight line across frequency, right? It's just completely let's see if I can zoom in here. Screw it. All right, whatever. Anyway, it's completely known in one domain, then it's completely unknown in the other domain. Okay, and this is what happens when you look at all signals, all information. Is that if you like and here this is like pretty much the most optimal situation where you don't know anywhere, but you know the probability is really strong that it's here, a little less that it's here, and then here the probability is here. So this is really close to what the Chebyshev polynomial is. Wow, I really need to increase the size of this thing here. Let's do it here like this. Okay. So you have the Chebyshev polynomial. It's a dot product. So a dot product is just divergence. It's how much one diverges from the other, right? So and you'll see that there's a lower limit on it, right? You can only ever get to this 1 over 4 pi squared, right? That's the closest you can get. This came out through mathematics. And then we have the same thing. I'll put it back here. We have the same thing with the uncertainty principle here with momentum and position. That there's this limit on it, just like this 1 over 4 pi squared. The limit is h bar over 2, which there's also a pi in the h bar. And we have the uncertainty principle. So the Fourier transform is really exactly the same thing as the uncertainty principle with particles. And so we have this link between waves and frequencies with particles that is represented like this. So if you really want to know something in one domain, if you really want to know its position, you have no idea what its momentum will be. And if you really want to know its momentum, you'll have no idea what this position would be because of this bound, this limit here, right? And the most accurate you can get on both position and frequency at the same time, knowing them both, is this. This is the closest you can get in that accuracy, okay? It's just this limit. And so this is information at its core, the structure of information at its core, and that's why we see it in the uncertainty principle, okay? So I already mentioned observation is information transfer. That's what observation is. It's getting information out of something. If you observe small particles, you can even destroy them, right? Like light, for example. If you observe light, if you want to observe a photon of light, the photon no longer exists. Doesn't exist. You've observed it, right? So you can only only observe for small particles. For large things, you can observe several properties at once because it's not really affected. But for small particles, you can only where you get down to the structure of information itself, where you're looking at information bits themselves, like the photon is just this small packet, this quanta of information, right? You can only observe one property at a time, right? You can only absorb information in one domain or the other domain. And if you absorb it in this domain, you don't know what the other domain was saying about it, right? And you can, So here, like if you absorbed it in this way, then you can absorb it sort of both ways and know, right? But if you absorb it really accurately in one domain, you have no idea what the other domain is saying. No idea, okay? That's sort of the principle. And yeah, the method of observation, how you observe something determines how energy is transferred, okay? So let's go into light. There's two types of particles. There's bosons and fermions. So light is a boson. Light's pretty easy for most people to understand it's just a photon is a simple packet of light, the smallest visible piece of light that you can get. We're not going to go into statistics. There's no time component to light, right? Light does not change in time because it's moving at the speed of light, right? We know this also from relativity. If you were to travel at the speed of light, your time would not change. You would not advance in time. You would be stuck in time and only move through space. All of your information will be in space. Interesting, right? So this is what light is like. Light, all of its information is in space. And if you move it to the frequency domain, you can sort of see what the energy level of that information is. It can be absorbed by fermions. It can be absorbed by other particles like electrons. Electrons can absorb light. Okay, and that's how you destroy the information, right? And the electron is very inaccurate in space and time. And so when you absorb light, you don't know where you absorbed it because you don't know where that electron was, right? Like if you ever want to absorb light and know where it was or when it was, you have no way of knowing because the thing that absorbs it is inaccurate in both realms as well. Okay. So this is how your eyes will observe. So your eyes have three kinds of cones. Okay, maybe I can make this bigger again just to see the picture. Right. So your eyes have three kinds of cones, and you're based on the frequency of light, it'll activate these cones. So you'll have electrons in these cones that are sensitive to this range of light and this range of light. So if you're both your L cones and M cones, right? These are the red cones, and these are the green cones. So if the ones that see red absorb it and the green ones absorb it equally, you'll get like this yellow in between, right? If only the M cones absorb it and a little bit of S and a little bit of L absorb it, then you'll see green, right? You'll observe it as green. And so this is how you're perceiving this frequency, okay? So in effect, you're not seeing the wave light as a wave, right? You're not seeing the oscillations of light. It's nearly impossible to see this. I don't know if it's just theoretical now that light has these frequential oscillations. It's really more theoretical. No one really ever observes this frequency of light. Okay, we know it from roundabout ways and things, but I don't have a picture here of what a packet is, but the theoretical packet of light is it just goes like this, and then the frequency gets larger, and then the frequency goes down, and then that's it. It's just like this packet of light that's moving. All right, that's the photon. Okay, so but the way we do observe it is with a frequency. So we don't know how it's fluctuating. We don't see the up and down of the electromagnetic spectrum. We don't see that, but we see the photon itself as a particle. We see it as a particle, and we absorb it as a particle. We absorb it as a single packet of energy, and we see it as a specific color in our eyes. Okay, and the same thing when you absorb it in a photo detector or something like that. You absorb it as a specific frequency, right? Okay. And you won't know exactly where, like I said, with the electron, you don't know where exactly it is and when exactly it is, because you don't know where and when the electron was. Okay. All right. So let's move on. Okay, so yeah, here, this is the same picture as before, but you'll see here, this is the time domain. So it's oscillating in time, this photon of light, okay? And how is it absorbed? Blip, like a blip like this, right? And obviously we don't get this because of the electron, but this is how we absorb it, okay? And this is something that I do every day when I do gamma spectroscopy, is you're absorbing really a wavelength of light. You're absorbing a very specific photon that's emitted from the nucleus of an atom. And this very specific photon has a very specific energy, and we get like this blip, right? We get a count every time. And then in gamma spectroscopy, what happens is one time maybe we'll get the count here. Even though we know it's very precise beam of light, we don't know how precise it is because of the fact that the electron isn't precise in absorbing it, or the germanium detector isn't precise in the energy it absorbs it. So it doesn't really know which frequency it was. We really don't know which frequency it was, and we don't know exactly what time it was absorbed, but we have like a range of time where we know it was absorbed, like based on your sampling rate. And then and that way we can see how much of a radioactive particle or radioactive substance there is in something that's giving out gamma waves. Okay, so it's just an example of how light is seen in the frequency domain. It's seen as like one blip, and we don't see this part. Okay, we can never ever observe this, but this we can observe. Okay. Okay, fermions. So fermions are the other type of particle, like electrons, protons, neutrons, and quarks. I put a question mark because we call them fermions anyways. There's the up quark, the down quark. Oh, okay. So they are present in both space and time. That's why they have the uncertainty principle associated with them, right? They share half of their time in space and half of their energy in space, half of their energy in time, right? If you were to cool it down to absolute zero, all of the energy of the fermion will be in a very specific location in space, but it will be spread out across all time, right? Like a fermion doesn't just disappear, it doesn't just vanish, right? It exists throughout all time, right? Unless it's annihilated, whatever. But like, I'm going to try to stay simple. So it's present across all time, right? All the particles in your body were present since the time of the Big Bang. Like that energy was present since the time of the Big Bang, and it's going to be present forever. It's just present throughout all time. But space, in space, it'll move. It'll move in space, right? It'll take up a really very accurate location in space, but time it'll be spread out. You won't know exactly when in time this particle is because it's throughout all time. But in space, you'll be able to really locate that particle, right? So that's just the idea of the fermion. And so you can't know the location and the momentum at the same time. Same thing, potential energy or kinetic energy, position velocity is the same as location momentum. So this is the uncertainty principle here. And then the observation is the interaction. What kind of energy are you transferring when you're observing it, right? So, for example, an electron can give off a photon, right? It'll give off information. And from that information, you can know something about the electron, right? But it's giving off, it's losing energy. And so that loss of energy, that transfer of information will affect the electron, right? That kind of thing. If you want to observe the electron in an interference pattern or something, you want to observe it in a very specific location, then you're taking all of the information into location, into space. And all of the information goes into space, and then you don't really know how much information was in frequency or in time. Okay? I have this here as well, so this is really gonna the Heisenberg uncertainty principle is really gonna dominate the fermion. Okay, all right. Now I'm gonna come out with a sound metaphor, just so because all of this stuff might have been a little bit over your head. So the best way that we as humans can understand this is through sound. Okay, because what our mind is doing when we are observing sound, when we are hearing sound, is our mind is doing this Fourier transform for us, okay? So, like, these are... Oh, I gotta make this big again. Okay. Okay, so you see this. You have A4. All of these are playing the A4 note, and you see the A4 note is here. It's like 440 hertz, right? You see this frequency peak. And this is what we hear. When you hear this flute, okay, you hear this note. You hear these peaks. This is an overtone. But that's what you hear. You hear frequencies. You hear timbre. You don't hear this oscillation of pressure, right? The pressure is oscillating in the air, and it's oscillating your ear, but you don't observe that oscillation. You don't observe the ups and downs, right? What you observe is a frequency, and you can recognize that frequency. And some people in the world have perfect pitch, and they can be like, that's an A. That's 440 hertz, right? And so these are different timbres, but it's the same thing. This frequency that's going up and down, you don't see that. This is what you see, or hear, right, in this case. Okay? And the same thing. So if you were to hear a drum beat, the drum beat, you will hear the drum beat as an oscillation, right? You get this drum beat going twice a second. So you hear it twice, you go bum, 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 bum. So you'll hear this oscillation. But if you increase the speed of the drum beat, increase it, and here we have hertz. So 440 hertz, that's 440 times per second, right? Like, look how many times this goes up in 1 second. This is 30 milliseconds, right? So if you get this going at a drum beat going at 400 times per second, you'll hear it as a note. You'll hear it as an A, 440 times per second. So this drum, if you slow it down, if you slow down this frequency, you'll start to hear the pressure wave. You'll start to hear the pressure wave, and it'll sound like a drum beat, okay? And so that's the perfect metaphor that I can give, is that your mind is doing this Fourier transform all the time and absorbing this sound as a frequency. Detecting it as a frequency, okay? Okay. Now let's get into cognition, because this is really the payoff here. So now that we understand all of this stuff, we can get into cognition. And cognition, we have the first thing in cognition, we have introversion versus extroversion. And so what we have is our subjective information processor is us, our subject. Okay. Now the subjective experience has we have a memory capacity. Okay, we have a processing capacity and a memory capacity. And that's it, like that, where our observations have to fit into that capacity, okay? And so we call this capacity awareness, okay? Now, what do I have here? We can only be aware within our information capacity, right? So the capacity of our awareness is this capacity we have to take in and process this information, okay? That's our awareness. And if we're focused on objective information outside of the subject, right? We're focused on what's going on around us. All the information we're taking in is coming in from the outside. we call this extroversion. Okay, this is extroverted process. It's objective. We're taking stuff in from the outside. It's extroverted, and our awareness is directed outwards, right? And if all of our awareness is directed inwards on our internal processes, right, it'll shut off all of the information coming in from the outside, and we'll be able to focus in on the inside, the subjective experience, and this is introversion. Okay. And so because we have this capacity, right, we have to choose. Are we observing subjective information or objective? Like, we have this capacity, just like this upper limit in the Heisenberg uncertainty, well, the uncertainty principle. We have this upper limit. That's our upper limit. We have a capacity for observing information, and this information can either come from outside or from inside, or from a combination of the two, right? From the subject or from the object. So if we're completely observing the subject, how much can we observe? Can we ever observe our entire subject, right? Is our awareness big enough to see our entire subjective information process? And the answer is no. And then we see this from emulation, right? One computer can't emulate itself, right? It has to emulate a lesser computer, right? So if you have like a really old video game system and you want to emulate it on a really old computer, it won't do well, but a newer computer will be able to emulate it well, okay? So that's the same thing. When you're looking inside, you have a capacity, right? And I say this here, that a file can never be larger than the hard drive, right? So if the file is bigger than a hard drive, it doesn't fit. It won't fit on the hard drive. So a file always has to be smaller than the hard drive. And so in our case, our subjective hard drive is looking at this itself, and it can't see more than itself, right? It doesn't have the capacity to see more than itself, and not even see itself entirely, because it is looking at itself. And by looking at itself, you are losing efficiency, okay? And so people who are really introverted and really subjective will have a very good picture of their subject, of their subjective information, but have a bad picture, and this is why it's mutually exclusive. They won't have the objective. So that's why there's either introvert or extrovert, or like somewhere in between. But you have to pick. You have to pick what you're observing at this time. Okay? And whatever you prefer, that's really usually what you're called, right? So if we dedicate our resources to be aware of subjective information, we call this awareness consciousness, okay? So consciousness is the introverted, when you're observing introvertedly, that's consciousness. Your consciousness is what you're observing when you're looking in. The consciousness is what is observing when you're looking out, but it's what you are observing when you're looking in. When it's looking at itself, right? So when you're looking in, your consciousness is looking at itself. When you're looking out, we call this awareness, because your consciousness is looking out. So you can see your consciousness if you're subject, okay? Sorry, oh. Yeah, so I said this here, a file can never be larger than a hard drive. The subject holds the information like the hard drive, so it can never observe a file larger than itself. The objective universe. Okay, so what about, can you ever observe the entire objective universe when you're looking out, right? That's another question. Like, you can't see your whole subject. Can you see the whole object if you're completely objective? And also no, the objective universe contains our subjective process within it, right? Our process is within the universe. So again, the subject, it can't observe all of reality because it would need more processing power than the universe itself, right? If the universe wants to completely observe itself, it needs at least the amount of processing power than the universe. It needs to be at least as large as the universe, right? So this is also one of the main criticism, one of the main failings of the simulation hypothesis, right? And there's ways to get around it, but the main qualm that most people have with it is that you can't simulate a universe more complicated than the original universe. You always have to simulate something less complicated. You always have to find shortcuts when you're simulating, right? So, some people say, okay, so we're not going to simulate a whole universe. We'll just simulate the human awareness, the human consciousness. And the human consciousness is what is simulated, not the universe itself around it, okay? So there's ways to get around it. But at least we know that the universe is not a simulation. Our consciousness might be, but the universe itself is not a simulation because you would need a larger universe in order to simulate it, right? Which, you know, there could be. It could be. But I mean, this is one of the failings. So yeah, the simulated universe must be less complex than the original universe that contains it. Okay. Intuition versus sensing. Now there's a huge connection here. Okay, so sensing information is similar to space-time. It's similar to this amplitude information, right? It's similar to these complicated waves, right? This sensing information, it's all of the little details of these waves, right? Details in time and details in space. The intuition will perceive information similar to frequency, okay? It'll miss all of these details, but it'll see the general pattern, the general frequency across these details. And the frequency is timeless, and it extends across all of space, right? And this is what we see before, right? So if you have all of this sensory data that you can't know here, right? It's just, you have no idea what it is. It's just really random and chaotic. If you use intuition, you'll be, I know what it is. It's really specific in intuition, right? It's that, okay? And the universe we live in is really right here. And really what we're doing is we're seeing about the same amount of information, just in two different ways, in a sensory way or in a intuitive way. So like, for example, sand on a beach, I'm using this as an example. So this is space information. So a sensory might perceive every grain of sand individually, right? And that's really hard on the processor. But intuition will perceive the pattern of sand, the frequential pattern, and disassociate it from space, okay? Same thing with time. So time, I used the beating of a drum as sort of an example. So the sensory will hear every beat in time. Okay, the sensory will hear the beat. It'll hear the quality of the beat and all that. But the intuition will hear the pattern of the beat in time. It'll hear the whole drum pattern. Like, it'll see this as repeating, and it'll divorce it from time. It'll divorce it from the dependence on time. Okay, so. And yeah, like, this is exactly what your mind is doing when you're hearing sound. It's doing this Fourier transform. So also the Fourier transform is present in sensory or intuition. How are you looking at the universe? Are you looking at it in sensory, or are you looking at it through intuition? Are you looking at it through space-time, or are you looking at it through frequency, right? And that's why this is just so fundamental to everything. And it's just the way we're perceiving information. Okay? And it's the same thing with electrons. You can absorb information in two different ways. Like, you can absorb it this way or absorb it that way, and depending on which one you absorb is how you're going to end up observing it. So it's the same thing. Are we absorbing information like this or like this? Intuition or sensing? So it's the same information. It's the same exact information. It's just doing a Fourier transform on it to convert it to one domain to the other. So it can be examined in separate but exclusive ways, right? So we know it's exclusive. If you observe it like this, you can't observe it like this. If you're a sensor, you can't really use your intuition. If you're using your intuition, you can't really use your sensing. It's the same exact process. So it's just like this uncertainty principle and the Fourier transform, okay? Okay, I guess this video is a little bit long and I spoke a little loud into my mic. I don't know, it's not. I had a mic problem, but anyway. Just like and subscribe. I hope I was able to give over this information. I didn't want to go too in-depth and too complex, but I also didn't want to go too simple because, like, I don't know who my audience really is. If my audience is physicists, then they'll be like, you were wrong there, you were wrong there, you're wrong there. I know. I didn't want to get too complicated. If my audience is like non-physicists, then this might be too complicated. So I hope it was understandable. And I hope you see that information theory is all pervasive. It's really our own minds, how we are observing reality, and how information is structured, and how this information structure determines how particles act with each other, because that's all we can see is this, and it determines how we understand information as well. Like, information is just something that's across the board in reality, and it could be more, but we can never know that. All right. Anyway. Have a good one. See you guys later. Bye.